Today in class you're going to be learning about earthquakes, just like the Great Haiti earthquake that you read an article about in class yesterday. Seismology is the study of earthquakes. Now, as we already know, most earthquakes occur at plate boundaries. You learned this when we were discussing plate tectonics and the different kinds of boundaries. A transform boundary is where you would most often see earthquakes. So how do these earthquake waves travel? Well, earthquake waves are called seismic waves. And the material in the earth doesn't actually move. It is the energy that travels through the material. And that material would be like the mantle material, the magma, the molten rock, which is pretty much the same thing as magma. And if you remember, we read or watched a video about how the seismic waves do not go through the core, and that's how they have an idea of what our inner core and outer core are made of. So there are two kinds of seismic waves. You've got body waves, which are the waves that go through the actual body of the earth, and then you've got surface waves. And the surface waves travel along the earth's surface. Now, with those body waves, you've got two different kinds of body waves, P waves and S waves. We'll talk a little bit more about those on the next slide. Alright, now the P waves. The P stands for two things, pressure or primary. We call them primary waves because they are the first waves to be detected. So primary meaning first. The primary waves can travel through solids, liquids, and gases. They are the fastest wave, and they move the rock back and forth. S waves are your shear or secondary waves. These S waves can't travel through liquid like the P waves do. And they are the second fastest wave. And instead of moving the rock back and forth like the P waves, they move the rock side to side, almost kind of like in an S motion. Look at these two pictures. The top one is showing you a P wave. This is your primary wave, and you can see it kind of makes sense that it travels the fastest because the energy just goes straight through. In the S wave, you can see how the energy rocks side to side and would probably take a little bit longer. Tomorrow in class, or later on today, we will be doing a demonstration with a slinky showing you how these waves move. Surface waves are a little bit different than the body waves. These move along Earth's surface instead of going through the Earth. They can travel up and down and back and forth. They travel slower than body waves, and they are generally more destructive than body waves. So the surface waves move along the surface and produce motion in the upper few kilometers of Earth's crust, so not really in the mantle like the body waves do. So now, how do scientists measure earthquakes? When you hear about an earthquake on the news, you are usually hearing about the magnitude of the earthquake. Scientists use seismographs, which are instruments located on Earth's surface that record the seismic waves. When they use the seismograph, they receive a seismogram, which would be a reading that shows a tracing of the earthquake motion created by the seismograph. So if you see in the picture, in that seismograph, there is a seismogram, and it has like the squiggly up and down motion. That is what you're looking at when scientists record earthquake motion. When an earthquake occurs, scientists refer to two different points of location for the earthquake. They talk about the epicenter, which is the point on Earth's surface directly above the earthquake starting point. So if we were talking about a city, and let's say we had an earthquake here in Georgia, and we said the earthquake was in Atlanta, Georgia, you would be referring to the epicenter of the earthquake. It's not exactly where the earthquake began, but it's the point directly above it. Now, the focus is the point inside the earth where the earthquake begins. That is where the seismic action is taking place. So this picture here shows you the focus and the epicenter. And as you can see, the focus is below Earth's surface, and that diagonal line is showing like where the fault is, where the two different plates move relative to each other, which would be your earthquake cause. And the epicenter is directly above it on Earth's surface. A measure of the strength of an earthquake is called magnitude. The Richter scale is what we use to measure the strength of an earthquake. So the Richter scale measures the ground motion from an earthquake and adjusts for distance to find its strength. Each time the magnitude increases by 1 unit, so like from 2 to 3, the measured ground motion becomes 10 times larger. So an earthquake with a magnitude of 5 on the Richter scale will produce 10 times as much ground motion as an earthquake with a magnitude of 4. So let's take a look at the table on this slide. If you notice, earthquakes with a magnitude of 2 to 2.9 are happening all the time, and it says that they are detected on a seismograph, but they are not really felt by people on Earth. So those are occurring all the time without us even knowing it, if there is an area where it might happen, like the plate boundaries are correct for that. Look at the great earthquakes with a magnitude of over 8. If you notice the number per year there, it's probably only about 1 or 2 a year. Those are very rare, and when they do happen, cause lots of destruction. We would hear about those more major earthquakes because of the destruction that they cause.
There are times when the Earth isn't as stable as it seems.
And it just kept coming, and it kept coming, and it kept coming again. And it was like riding a roller coaster. It was really a rocking and rolling. I just, in my wildest imagination, had no comprehension that Mother Nature could be that destructive in just,
Every year, more than 1 million earthquakes rattle our world. We don't notice most of them, but the ones we do give us new respect for our planet. Earthquakes happen when tension stored in the Earth's crust is suddenly released. To understand what causes these disasters, we need to travel to the center of the Earth. The enormous heat and energy here shapes the layers above, especially the Earth's outer crust. We can think of the crust as a jigsaw puzzle divided into about 12 tectonic plates. These giant slabs of rock hold the continents and the ocean floor. For millions of years they've been drifting and colliding, pushed by the churning liquid mantle below. When they slip, grind, and crunch past each other, disasters occur. Some of the worst quakes happen when the plates get stuck and pressure builds. When they finally break free, energy is released as waves traveling through the ground. Geologist David Schwartz describes the process.
The plates are moving past each other. They're pushing against each other. When the stress builds up to a critical point, they snap, and the snapping of the plates basically produces the seismic waves that's the earthquake.
These disasters usually occur at the boundaries between two plates. This is where we find faults, cracks and fractures in the Earth's crust where the plates inch along. Geophysicist Ross Stein explains.
These faults, typically at their base, let's say 10 miles down, are moving at a few inches a year. And when that earthquake occurs, when that rupture begins, that fault, that motion is going to accelerate from a few inches a year to about 5,000 miles an hour. And it's going to do that in 3 seconds. So this rupture of the fault is a catastrophic process, unlike hardly anything else in nature.
Like ripples in water, the vibrations spread out in all directions, shaking everything in their path. The strongest shaking occurs at the epicenter, the place on the Earth's surface directly above the spot where the earthquake began. One of the worst quakes on record struck Alaska in 1964. It measured 8.5 on the Richter scale, a scale that measures the magnitude of a quake. The shaking lasted around 4 minutes, which is a long time for an earthquake. The ground ripped open, and in some places sank more than 50 feet. We know how earthquakes happen and the great destruction they create. But unfortunately, we still can't predict them.
When you have finished the earthquake notes, please read pages 230 to 239 in your textbook. Make sure when you're reading that you are paying attention to how to measure an earthquake. Take a look at the graphs on the pages. And then in section 3, that starts on page 234, there's some interesting information about earthquakes and earthquake-resistant buildings, which kind of goes along with what we did when we did our column capers lab.